Thank you, Anne, and thank you, Peter. It's really an honor to be here, and thank you all for attending this lecture. I wanted to talk about mitigating near-term climate and advancing human development at the same time. And kind of the first question that might come to your mind is really, why do we care about near-term climate anyway? And so I'd like to just spend a moment to motivate why this is an issue. Climate change is obviously going to be a major problem in the future on our current pathway, but it's also a problem now. And in 2100, things will be worse, but look what's happening already. This shows the sea ice decline in the Arctic. Is that blue line there on the bottom? Most of you are probably familiar with that. It's been widely reported, this dramatic change. And look at the red one above it, the snow cover in the northern hemisphere in June from a paper that just came out earlier this year. 2/3 gone in the last few decades. So this is going to be entirely, wiped out within the next few decades if this rate continues, long, long before 2100. Things are changing rapidly already. Whoa. See? I'm sorry, it's all doom and gloom and everything goes black right away. Okay, woken up. This is a bit of a complicated plot, but from a paper Jim Hansen just published earlier this year. And I just want to call your attention to these lines here in the orange, the red. Let's see, maybe I even have a pointer here. Yep, the orange, the red, and then the black. What he's done here, I'm not quite sure why it's doing that. What he's done is to look at the days 2 standard deviations and 3 standard deviations above the normal. And the normal really here isn't defined in any extreme way. It's not back a long time ago. It's the middle of the 20th century. And so there's this middle line there on each side, the red one, that shows the kind of hot summer you would get roughly, say, 1% to 2% of the time in the middle of the 20th century. Now you're getting this almost a third of the planet. This is already, what used to be a very extreme summer is now rapidly becoming a very normal summer. What's happening is not just confined to temperature and the cryosphere. This shows the rainfall trends for the last 50 years during the wet season in South Asia and East Africa from the CRU data set. And you can see that East Africa, decrease in rainfall, parts of India decreases in rainfall, and Southeast Asia. These are pretty substantial changes, and these are areas where agriculture is largely rain-fed. These are developing nations where people are subsisting on the products of this agriculture. So for them, these changes are already very important. So near-term climate change is an issue as well as long-term climate change. Now, what's driving climate change? Most of you have probably seen this more times than you'd care to acknowledge. But this is actually a slightly different version that people usually show from the AR4. This is attributing climate change by emissions of different compounds rather than the concentration changes. And CO2 is this bar up at the very top. Obviously, CO2 is the biggest player. Nobody is questioning that. But you've got some other pretty large contributors to warming. And the 3 that really stand out here are these 3, methane, carbon monoxide, and black carbon. And if you add these up, you find that these are not a negligible fraction. These are about the same magnitude as the total forcing from CO2 in the past. But they're not equivalent to CO2 in many respects. One of those respects is that they degrade air quality, whereas CO2 doesn't. You don't want to be breathing in these things or their direct chemical products. The other is that these have a very different lifetime than CO2. This makes them really a distinct class of warming agents from CO2. And so just with that chart in mind, it's kind of clear that ideally, if you were able to remove one of these, black carbon, carbon monoxide, methane, or other ozone precursors, you would improve air quality and you would reduce the rate of warming. I think that much is pretty uncontroversial, but rather, in an ideal world, you can do this. You can do this easily in a model. In the real world, you can't do this. So while people had been talking about this, and it had been getting increasing political attention, there was really a need to figure out what can we really do with the know-how we have. There was kind of a bottom-up upwelling from the high political echelons for somebody to answer this question, and the job fell to UNEP, the United Nations Environment Program with the World Meteorological Organization, who agreed to try and find out, are there really practical ways, not idealized ways where you wipe out black carbon magically with your magic wand that only affects black carbon, but real things you can do that affect lots of different pollutants, that we have technology. What can actually be put into place? So UNEP WMO agreed to try and find this out. Being rather naive about the amount of work that it would take, I agreed to chair this report. And so I'm going to talk for a lot of the rest of this about some of the results of this work. This is a really very interdisciplinary group of people that UNEP got together, both across different parts of physical science, epidemiologists, agriculture specialists, economists, and we did a lot of work together, and I think we came up with some pretty interesting results. In a nutshell, the method and the approach that we tried to follow was to look at those existing technologies that we know would improve air quality, reduce emissions that lead to degraded air quality, and those that would reduce rates of warming. And so the real question was, what is the overlap between these two? Is it so small that this isn't an issue we need to worry about, or is it big enough that you could actually, there's a large area overlapping in that diagram that can really get you gains in both of these areas? So JASA in Austria has a database with about 400 different technological measures that have already been put into place somewhere in the world. The results have been measured. We know what they do to emissions, more or less, and we can look at what the effect would be if you put any of those 400 measures into place worldwide, aggressively, rapidly. You'd see what the maximum benefit you could get. Some of those measures are not necessarily going to lead to warming. Some of them will. So what we did was we looked at all 400 and we ranked them by the GWP, the global warming potential of all of the different compounds that are emitted or affected by any of these measures, and we picked the top for further study. So I'm going to tell you what one of the key findings is, what are the top measures with potential for gains in both air quality and climate change. And there are really two classes. The first class concerns methane. There's a group of methane measures that deal with extraction and long-distance transport of fossil fuels, so coal mining, long-distance natural gas pipelines, natural gas storage, which is what you're seeing there on the bottom. The left is a visible wavelength photograph of a storage tank in the southern U.S., and the right is an infrared tank, which gives you the nice illustration of why these are powerful greenhouse gases, and also just how much leaks out without us knowing about it. You notice that this is not fossil fuel combustion. This is different. This is the fossil fuel sector, but it is not related to electricity generation and combustion. The others are not the fossil fuel sector at all. They're waste management, municipal waste, landfills, wastewater, and they're the agricultural sector, dealing with livestock manure and rice cultivation, which are substantial sources of methane. The second set are measures that for short I'll refer to as black carbon measures, but in fact, they actually reduce emissions of black carbon and everything that comes along with it. Some of the most important ones of which are organic carbon and carbon monoxide. And there's a variety of these, about 9 and particularly important ones: reducing emissions from diesel vehicles, tighter standards, particle filters, that sort of thing. Replacing coal, which is still used in many parts of Asia and Eastern Europe in residential stoves for cooking and heating. Replacing wood burning in industrialized countries. So many of these measures are in developing countries, but not all of them. Using clean burning cook stoves in developing countries. So the lower right-hand picture, you see a woman cooking over a traditional fire, very inefficient, but done by billions of people every day. And replacing gives you something, not extremely high-tech, but nonetheless much cleaner burning and more efficient. And then there's small industry like brick kilns and coke ovens, almost all in the developing world. And there's open burning of agricultural waste, which is, for example, banned in the EU, but permitted to some extent in North America and permitted to a great extent in many other parts of the world. These are the 9 plus 7 measures that we came up with that seemed most amenable to producing gains in both near-term climate change and air quality. So these we studied in further detail. This shows what these do to emissions, with the upper bar in each case being a reference projection of what the emissions are likely to be in 2030, and the lower the impact of the different sets of measures. The black carbon measures then, you put these 9 measures together. While there were 400 in our database, these are really getting you the bulk of the signal. You've got about 80% reduction in black carbon here. But at the same time, you've reduced organic carbon and carbon monoxide pretty substantially. So these idealized cases where you just take out black carbon, that's not going to happen, and it's not going to tell you what the net effect is. I'll come back to this, and this is an important factor in the uncertainty in the response to the black carbon measures. Distinct from those, the methane measures pretty much just affect methane. And there you see that you reduce what's a projected increase in methane due to increasing exploitation of natural gas primarily. You turn that into a decrease, about 40%. There's plenty of areas of methane, the direct methane from cows, we're not that far along. There are feed additives, but there's a lot of things we can't do. We don't have the technology to achieve quite as large reductions, or they're only about half as large for methane as for the black carbon, but it's still a pretty big difference, 40%. And you can see down there the bottom 3 sets of bars, sulfur, NOx. There's an effect on NOx, but it doesn't have a great effect on climate. There's hardly any effect on sulfur, and there's hardly any effect on carbon dioxide. And that's because you'll remember that these measures are not targeting the main sources of carbon dioxide. They're not targeting the total driving from vehicles. Even when vehicles are involved, it's only particulate controls on diesel. And when we look at power plant, well, we're not dealing with power plants at all, really. Power plants are so efficient in their combustion, it's at such high temperatures that they emit very, very little black carbon. Well, very different kinds of things we're looking at here. This was our, then, calculation of the impact on global mean climate. What you see here are 4 different sets. Maybe I can use that. There we go. I can use this instead of the pointer. So there's a reference case where business as usual emissions just kind of continue to follow the trajectory. Actually, this is from the International Energy Agency. Temperature just goes up and up and up. Instead, if you apply, I've lost it again. All right, the next curve down, labeled CO2 measures. This is a case where what we've looked at is the International Energy Agency forecasting what would happen if the world adopted and followed a path leading to 450 parts per million CO2 in 2100. And what you see is actually that goes slightly above the reference case in the near term. What you're doing when you're targeting CO2 is you're influencing primarily sulfur. And you get a fast response from sulfur, which actually gives you a little additional warming in the near term. But in the long term, of course, you look at the rate of change there, and that curve that was going inexorably up in the reference case is really bent over. You've really had a big effect on long-term warming, but you've had virtually no effect or even a slight disbenefit in the near term. And in contrast, when you look at the methane and BC measures, you see all the benefit is in the near term. The long-term response, when you get out past about 2050, is basically the same rate of change as you get in the reference case. But in the near term, the rate of warming over the next 30 to 40 years is cut in half. So this is not a way to reverse the warming. It's not a way to even flatten it out. It's going up too quickly for that. But we can at least cut that rate down in half. And then the last curve there in the yellow, you can see that only when you put them both kinds of controls together, you deal with both the short-lived pollutants and CO2. That's the only one of these that stays below 2 degrees C. Just to kind of explore a little bit further the relationship between the near term and the long term, this shows the same 2 curves up on the top and bottom, the reference and the impact of imposing these methane and BC measures, starting immediately. And then in the middle you see what's the impact if we wait about 20 years and impose the measures on black carbon and BC later. If we do that, and then you look out in the distant future, you see that really you get almost the same benefit. It's a little bit better to do it early on, but it's not that much better. And so when you're really worried about something like the long-term temperature target or what temperature change is going to be in 2100, CO2 is the only way that you really have a lot of leverage over that. What you do see is that putting these measures into place early on gives you this much reduced change in temperatures over the next few decades. And so this is really a motivation to do this for its own benefit in the near term. There's no real urgency to tackle short-lived pollutants for the sake of meeting a long-term temperature target. In contrast, there is a real urgency to tackle CO2 right away for the sake of a long-term temperature target because it lasts so long in the atmosphere. But that's not the reason for urgency to deal with these pollutants. The reason to deal with these pollutants is for realizing their benefit in the near term, which is what I was trying to show you at the beginning. Climate change is already happening now. It's already upon us, and so there are good reasons to try to realize this benefit in the near term. Now, everything I've shown so far is restricted to global mean temperature, but we also did analyses with full climate models. The previous analyses were done with the model we use at GISS and a model run in Europe, the ECHA model. So we had some way to test the robustness of the simulations. These are from full coupled ocean atmosphere simulations with the GISS model. And I really just want to make 2 points here. The lower panel shows the temperature response. On the right are just the methane measures, so that package of 7 measures. And on the left are the methane plus the black carbon measures imposed together. And what you can see is while each one of these contributes to reducing the rate of warming, so temperatures are cold relative to the reference, there's much more regional inhomogeneity when it comes to the black carbon measures. And in particular, there's a noticeable enhancement in many of the snow and ice covered regions. And that's partially because the black carbon deposits on these formerly bright snow and ice surfaces, instead of reflecting radiation, they absorb radiation, and you get this extra albedo forcing leading to enhanced response in certain regions. So the global mean, obviously you lose that kind of representation. There's a substantial difference when it comes to the regional scale. In the upper panel, we're showing rainfall changes, again due to the 2 packages of measures. And in this one, what we've done is the radiative forcing imposed is almost exactly doubled, going from the right methane only to the left methane plus black carbon. And the temperature scale there of that color bar is exactly doubled. So if you had the same proportionate rainfall response to radiative forcing, you would see the exact same colors on both sides. And what you see is there's some similarity in the spatial patterns of which regions get wetter and which regions get drier. But in fact, the colors are much darker on the left. And so proportionate to the radiative forcing, which is what's going to govern the global mean temperature change, you don't get a good picture of the rainfall impacts. And in fact, the impacts on precipitation are much, much larger for the aerosols per unit forcing than they are for a well-mixed greenhouse gas. And you can see areas like the Sahel in Africa and Southeast Asia, some of the areas where I was showing you that the observed trends are large. You can see that the aerosols are really dominating what's going on in these simulations. And that's not restricted to just these simulations. We have some other results where we looked at the impact of all kinds of different individual radiative forcing agents. You don't have to follow exactly which one is which in all of these. I'll point out the key ones. This is showing Southwest China and Southeast Asia, where you can see the farthest right point in each of these panels is the observations. And you can see that the observations are this drying of Southeast Asia that I showed you in the CRU data early on. And what happens is the greenhouse gases give you, in fact, increased rainfall in that region. Not only do they not give you the observations, they give you, in fact, the exact opposite of the observations. In the Sahel is another region where we've seen substantial droughts. Again, the observations show this distinct drying trend over on the far right, and there the greenhouse gases give you hardly any signal. If you look instead at the impact of aerosols, there are a couple different points depending on whether you include indirect effects or just direct effects, but you can see the aerosols are really giving you something that's much more representative of what we see in the real world. So that historically, it appears that the aerosol forcing may have really been the dominant factor in some of these regional rainfall trends. And results from other models seem to show qualitatively similar behavior, that the response per unit forcing to aerosols is larger in many regions. This is the GFDL model looked at northeastern India. The observed trend was a pronounced drying. Aerosols gave you a pronounced, though not as big as the observed, drying, whereas greenhouse gases gave you a increase in rainfall. So I think I won't go through too many different models here, but I think we don't have a sense that the exact values projected by any model are very robust at the regional scale at this point, but we are getting a sense that the model result that the response to aerosols is proportionately larger than the response to greenhouse gases. That does seem to be a robust feature of a variety of climate models. So I've talked a little bit about the global mean temperature impact, the regional temperature impact, and the regional precipitation impact. But of course, the motivation for this study was also to look at the effect of air quality. So we also used the results from the model PM 2.5, so particulate matter less than 2.5 microns in diameter, and ozone concentrations at the surface from both the GISS and ECHM global models. And we use these with epidemiological and concentration response relationships from the ecosystem studies, looking at the impacts of these pollutants on human health and on agriculture. And just an illustration of that, down there at the bottom, you can see I think that's Manila on the right. You can see the air quality is abysmal at times in some places, especially in the developing world. And you can see what that does to crops. The three plants there, the one on the right is wheat grown in the ambient air seen in Pakistan, I think in Karachi. And then if you clean the air, look what it does to the wheat yield. So these are not relationships that we really have any doubt about. We might have some quibbles over exactly what the concentration responses are at high dosages, how they work for every different cultivar and every different crop, but we know that there are powerful effects of these pollutants, both on our ability to grow food and on human health. And so this shows several of the different impacts of these short-lived pollutant reduction measures. Again, on the top there is the climate change, and you can see that this regional difference that we talked about with the especially large benefits over bright albedo surfaces in general. In the middle there, though, you see that the regional pattern has become much more distinct. And what we're seeing now is that we have more than 3 million premature deaths prevented every year if these measures are put into place. And you see that most of these benefits occur in the developing world. So where there were measures that were targeting things like the wood-burning stoves in industrialized northern countries, but most of the benefit for human health comes about from reduced particulate, and that's mostly from emissions in the developing world. So the developing world, or in even more broadly, those areas that take aggressive action to reduce their emissions are the ones that reap the largest benefits in terms of premature health. So that's clearly not the case in terms of temperature change. It is probably somewhat the case in terms of precipitation, reducing disruption of traditional precipitation patterns, but it is very clearly the case when you get to human health. It's in the interest of nations to do this for their own sake, and the climate benefits can come along as the extra, whereas that perspective might be different for reducing something like CO2 or methane. On the bottom, crop yield improvements, not quite as localized to the regions where reductions are made, because now you have an influence of where there's available sunlight to generate ozone, which is the primary player here in crop yields. But you can see in sunny regions like the Middle East, Mexico, you get very strong benefits from reducing these pollutants, and more than 50 million tons just in 4 staple crops would be the increased yield every year from these benefits, from these emission control measures, rather. Now, this tries to encompass a lot of these different impacts in one representation, and that's, of course, hard to do. Now we've sacrificed the spatial information, But there's some pretty interesting things revealed here too. And if you look at the left panel, we see the impact on climate change, the avoided warming in 2050 in degrees C. And the bar on the left is the impact of the methane measures. The bar on the right is the methane plus, adding in the BC measures. And what's key here is that kind of reddish-colored uncertainty range. What you see is that in our best estimate, each of these accounts for roughly about half of the benefits in terms of global mean climate. But you see that the uncertainty range is much, much larger for the black carbon measures than it is for the methane measures. And that's because you have the net impact of these measures is the residual between a positive forcing from black carbon, a positive forcing from reduced carbon monoxide, but a negative forcing from reduced organic carbon. And so you see that the error bar actually overlaps the benefit from the methane measures. It's possible, it's not likely, but it's possible you would get very little benefit from the black carbon measures just because many of the aerosol processes that are governing the radiative forcing have such large uncertainties that we can't rule that out. You know, by far the bulk of the area under the probability distribution of what the radiative forcing is positive, and these would give you benefits. I think we have enough confidence in that to make that a worthwhile goal. But we can't say for certain that wouldn't happen. I think we have even more confidence that these would reduce disruption of traditional rainfall patterns, but that one's hard to show in a bar graph. So if we move to the middle panel, for human health, now you see actually a different story compared to the impacts of climate change. When it comes to human health, while ozone is toxic and there's a clear benefit from reducing methane via reductions in surface level ozone, the benefits from reducing particulate are so large that it's hard to even see the methane benefits on the same scale. And so while we have more confidence in the global mean climate benefits of methane, we actually have more confidence when it gets to the human health benefits that the BC measures are the right target. And with food security, this is coming about primarily because of ozone, and the BC measures are primarily giving you a benefit via carbon monoxide, so you don't really have an offsetting effect there. You end up getting the net effect of the carbon monoxide and methane measures is about equal, so about 50-50 here for these two sets of measures. But if you were more interested in health, you would probably favor the BC measures, and if you were more interested in global mean climate, you would probably favor the methane measures. If you do look at the methane measures, given that methane emitted anywhere in the world has the same impact as methane emitted anywhere else, we can actually provide policymakers with a very, very detailed list of where the potential reductions are. We can do this by every region on the world and by every sector that's emitting these. And so you can see, for example, that top bar of China has a very large orange segment, which is coal mines. And of course, there's always room for improving the emission inventories, but you can kind of really drill down into exactly where you could apply increased technology for emissions reductions or regulations for emissions reductions to achieve the greatest gains. Unfortunately, that's not so easily done with the black carbon measures because their emissions from any location are not equivalent to emissions from any other location. And so that's something where still a good deal of work, I think, is really needed by the community to figure out where policymakers would ideally target amongst those 7 or 9 measures that we listed. Now, we tried to further provide useful information to policymakers by doing economic analyses as well. And of course, this is always somewhat challenging. There are ethical issues raised, as well as no clear consensus on how to value something like climate change. Nonetheless, so these numbers all come with substantial uncertainty bars, but nonetheless, policymakers really like to know the relative cost and benefits of emissions mitigation. Of course, that does and should figure into their decision making. So for the methane measures, when we looked at the total valuation of these in billions of dollars US, I think the relevant thing here, more than the precise numbers, is that the climate benefits were the largest component. But the health benefits, even though they were not so easily visible compared to the PM-mediated benefits, they are about half the size of the health benefits. So that means if you're working under the assumption that methane behaves just like any other greenhouse gas, and you should just compare it with reductions in, say, nitrous oxide or SF6 or something else, based on its climate impact, you're missing quite a lot of the benefit that's obtained via methane reductions, at least about half from an economic point of view. If you then turn this, given that emissions of methane from any place are equivalent, if you turn this into a valuation by ton, you come up with a number of around $3,500 per ton. And we were quite pleased to see a number like that, because there's been a lot of work done on the cost of putting these measures into place. You remember that these are not things like carbon capture and sequestration or air capture or something that is being worked on. These are things that have been put into place in the real world, and we know how much they cost. They've been done. We have the data. And when you look at them, of course, there's a curve. They don't all cost the same amount. But the typical abatement measure is less than $250 a ton. One of the reasons that these come out with fairly small numbers is because, unlike, say, CO2, when you capture methane, especially if you're capturing it, say, from the fossil fuel extraction and distribution process, you have a commodity to sell. That changes the economics quite dramatically. If you're the person that runs a long-distance natural gas transmission pipeline, if you stop the leaks, you have more commodity to sell. And so some of these have negative cost. But even looking at a threshold of, say, about $250 a ton, we get about 3/4 of these measures fall under that. So therefore, the benefits are more than an order of magnitude larger, despite the uncertainties associated with valuation of how much premature mortality costs, et cetera. We can see that the benefits greatly outweigh the costs. Obviously, the problem here, like with so many things, is that the person getting the benefits is not necessarily the person paying the costs. So this doesn't mean that, I mean, if it was so simple, it would have been done already, right? But from a societal point of view, the benefits are much larger. For black carbon, the climate benefits are again substantial. They're comparable in size to the magnitude of the methane benefits. But now the health effect is just so large that it dwarfs all of the other impacts. This is huge. And this is independent of whether you use a uniform valuation around the planet or you tie the valuation of premature death to the local economy. This is a really big number, no matter how you do it. Again, you have this issue that the person paying the health costs is not the person imposing these measures. But from a societal point of view, the benefits are absolutely enormous from imposing the BC measures. And again, the costs can be very low. For more than half the measures, there's a net cost saving. And for another about 25%, the banning of agricultural waste burning or taking high-emitting vehicles off the road. These are largely regulatory policies with some enforcement costs, but much less of an economic cost than, say, heavily investing in new technology. So the economics for both kinds of measures can be very, very favorable. There's associated benefits to human development. If you think back to the title, what I'm really trying to get at here is that if you just think about climate change, or if you just think about air quality, you might not choose any of these measures. But if you think about the larger perspective where multiple impacts come into place, these become very attractive. And the economic analysis includes several of those, but it doesn't include these extra development benefits. If you change to clean burning cook stoves, you reduce the amount of fuel that needs to be collected. And if you go to many developing nations, you see that women and often children spend a huge part of their time going into the woods collecting biomass for cooking. So they don't have time to go to school. They don't have time to start a small business. And they're causing massive deforestation. That can be prevented if they're brought out of energy poverty and provided with access to modern fuels. And that has been done. It's been done in Senegal, for example. It's not trivial, it's not easy, but it can be done and reaps a whole host of benefits. But since it affects so many different factors of society, it really needs the input from the Education Ministry and the Health Ministry and the Environment Ministry, etc. There's all the multiple benefits that go along with it. The same kind of argument can be made for the cook stoves or the kilns or the coke ovens. In developing nations, the main way to improve these is to make them more efficient. So this shows some brick kilns in Mexico. The one on the left is a traditional kiln with all kinds of black smoke pouring out of it, and the one on right is a modern kiln which cost really no more to build. It costs a little bit of training to figure out how to use it. Once you figure out how to use it, since it's more efficient, remember that's how we reduce black carbon. We combust more efficiently. It uses only half the fuel of the other. This saves a lot of money. It saves a lot of time. The bricks are produced in half the time, and the people that get these love them. They think they're the greatest thing, ever. But it takes a real concerted effort to go out and put into place thousands and thousands and thousands of these small industries. With methane capture, I've already mentioned, you have a commodity to sell, but you also do things like increase energy security. The example here is a methane capture plant put on the city dump outside of Monterrey in Mexico. And they get enough methane from that to power their entire rapid transit system. Means less imports, less dependence on imports, and of course, reduce carbon emissions. So there are a lot of other benefits which are not even included in the analyses that I've shown so far, which already show that these were quite favorable from an economic point of view. They're also very favorable from a human development point of view. So how can we get these put into place? Well, I've mentioned a couple times, these are already in use. These don't require technological development, but they do require policy work. We need a much wider and more rapid implementation, and in many cases, the initial capital investment, even for the economically favorable ones, can really be a hurdle. So there are a lot of different ways to do that. The CDM, the Clean Development Mechanism under the UNFCCC, includes methane, since that's a Kyoto gas. And so that's an example of a very, very large-scale international financing effort, which funded this coal mine methane recovery project in China on the left. And you can go all the way down to the opposite end, where on the right, a small manufacturer of efficient charcoal cook stoves in Ghana actually gives all of the customers a loan to buy these stoves, because people don't have the money to buy these stoves. Collecting wood and using a few rocks, or buying the wood, doesn't cost any money up front. And so they need a loan, they get a loan, they buy less fuel because it's more efficient, and every week they put a few of the coins that they save from not having to buy as much fuel into that little box, which is attached to the stove, and after a year or so they're able to pay back their loan. So a kind of macro finance all the way down to microfinance, but the really innovative techniques for making these things, which are in the long run economically favorable, but innovative techniques for getting over that implementation barrier are really needed. The science really says, at least from my point of view, some interesting things about how to go about reducing these pollutants and how to consider them with respect to other climate-altering pollutants. Methane, of course, is already part of the UNFCCC negotiations. It might make sense to just keep that there. It might make sense to pull it out. One of the problems with that is that the exchange rate is only including the 100-year climate impact, and it's ignoring everything else. So it's not necessarily an ideal way to get the 100-year goal. It's a single endpoint focused kind of analysis. For black carbon measures, there are really very distinct differences with respect to the well-mixed greenhouse gases, and therefore these lead to very significant differences, I think, in the policies that should be implied. It's not part of the Kyoto Protocol, and the benefits are really very localized compared to what you get for a well-mixed greenhouse gas, and the health benefits are really even larger from let's say, an economic point of view than the climate benefits. So well-mixed greenhouse gases, what this leads to is a common These are a common good. Anybody that reduces them, of course, the benefits are spread around the world. So this really incentivizes doing less and encouraging others to do more. And if you look at the UNFCCC negotiations, well, that's exactly the kind of argument you get all the time. No, you should do first. No, we're not doing anything till you do something. And everybody's pointing fingers partially because they get the benefit from anybody else taking action. But that's not the same when you get to these BC measures. And the local good means that it's in each state's own interest, not to argue with the others, but to reduce their own emissions. And the health is really an important issue everywhere, even more so than climate change in many parts of the world. So this kind of leads to what I would say are some fairly clear implications. Just going back again, remembering that CO2 and methane in BC are really from different sources, and they have impacts on climate change on very, very different timescales. That would argue for a two-pronged strategy where we really do not attempt to link these, we don't attempt to trade these, but we attempt to have a long-term climate stabilization target, which is mostly going to be about CO2 to avoid disastrous changes in the longer timescales. And we have a near-term target, which is really closely linked to human development and not just about climate change. To remind you again why I think that there's will around the world to target near-term climate change. People are already suffering from these impacts. Biodiversity loss is much more closely linked from many studies to the rate of change rather than the total. So slowing down that rate over the next 40 years gives species much more chance to adapt, provides additional time for humans to adapt to these changes as well. And of course, to realize the health and agricultural benefits means this is a useful second target alongside reducing CO2. Not instead of, by any means, but alongside. And there's been an effort now to do that. Hillary Clinton launched a climate and clean air coalition earlier this year. And the media coverage I thought was really rather interesting, that in the United States, just an example there from the New York Times, it was all about the climate, why this was a nice thing to do because of climate. But then when you looked in South Asia, climate and saving lives. And I think that is really just perfectly fine. I think people could join a coalition like this with entirely different goals foremost in their mind, but they're all working in the same direction. And so it really facilitates that thing. This local good means that countries want to join it. Other countries, even that aren't getting the local good and might be more concerned with the global climate, like the United States, are also interested in joining, and everybody's pushing in the same direction. And this coalition is now up to 18 nations, which hopefully will do something good. So I would say, if I leave you with just a couple bits of information in mind, I think that both short-lived climate pollutants, as the State Department decided they should be called, thinking people probably accurately don't know what forcers are, short-lived climate pollutants and carbon dioxide, both important things to reduce, both important to reduce now. Carbon dioxide, the reductions need to start now because it lasts a long time. Short-lived climate pollutants because people are dying from breathing these in, and because they're really the only leverage we have on the near term. So these are distinct societal goals. I think we can and should do both. And I hope that there's, even while they're distinct from a science point of view, from a political point of view, maybe having a broader perspective that takes into account more impacts than just climate would even help motivate the CO2 negotiations. People talk about the green economy and how this gets connected to other things, but primarily the focus has been we need to reduce CO2 for climate, and we can see that that really hasn't gotten as far as we'd hoped. So I think that the physical science community, we should be actually rather proud that we have brought together information from lots of different parts of physical science, from ecosystems and air quality, health and climate, and we put all this together and given policymakers the tools they need. And I think now that we have that information, really we need to target near-term climate change for the sake of our generation and our children's generation. And we need to target long-term climate change too. I don't think either of these groups should be neglected. I don't want to even discuss which is more important than the other, but I think it's clear both of these generations are important. Thank you very much.
try to see. We have time for some questions. Right here. Here's one right there. Yeah, right there.
Wildfire-prone area. I have noticed, I know that it's usually perceived as a source of CO, but I know the health effects must be tremendous, both health effects in both black carbon and CO. You want to offer any comments on wildfire suppression or impacts?
Right, so the question is about the impacts of wildfires, and actually that's an excellent question, because one of the responses I got after our study on this came out in Science last year was some of the groups pushing for reduced deforestation, saying, oh, so should we not pay attention to wildfires? It's not on your list. And just because something's not on the list doesn't mean that it's not important. I think the results from looking at the impact of agricultural waste burning indicate that that would be a good thing if we could reduce wildfires as well. But there's this whole issue of how much of wildfires are caused by human activity versus how much are natural, how much control do we really have over that. And that didn't really fall under our technological or regulatory approach that we could deal with. But I think it's clear that that would be a substantial benefit, and there are many sources of PM from wildfires which I think are going to be even a bigger health hazard than the CO that leads to ozone.
Here's one right here.
Yes, thank you. I was very happy to see a nod in the direction of the need for a two-pronged approach to short-lived versus long-lived, but I still think your analysis vastly overstates the climate benefits of reducing the short-lived sources, especially methane, because it assumes that the methane efforts will not detract at all from efforts to reduce the CO2 in the long term. And you also assume the world more or less ends in 2070. So Susan Solomon and I attempted to take an initial look at what happens out in the longer term. We found that if the methane efforts take away from CO2 on a GWP 100 equivalence, then you buy a relatively small short-term benefit at the cost of a very, very large long-term deterioration in the climate. And I think that more attention needs to be paid on the extent to which these efforts will have the perverse effect of taking away from efforts to reduce CO2. That's not so much an issue for the soot, but it's a big issue for the methane.
Right, so the question or comment really is if these measures would take away from efforts to deal with CO2, that would of course have adverse effects on long-term climate. And I fully agree that that is clearly the case if these measures were to do that. I think you're right, it's not really a question for physical science, but I think that, and that's one of the reasons where I even suggested that maybe we should consider taking methane out of the Kyoto Protocol and not trade it with CO2 the way it's already done, just to avoid the possibility of people thinking that these are equivalent. But I don't think that necessarily one has to come at the expense of another. I mean, what we really need to do is put a price on carbon, of course. And if we do that, we can start to bring down CO2. These are really tackling a whole different kind of measure, or different kind of activity, and bringing together different sets of institutions. I mean, the main reason you're going to do a lot of these, and even the people doing them, are not necessarily going to be the same people that deal with climate. You have in many countries, and this is one of the difficulties with getting these kind of measures put into place, is that the responsibility spans many different parts of government. So those in charge of air quality have to work with those in charge of human development and deforestation and Department of Interior type land management. These all have to work together to get this kind of thing done. Whereas CO2 can, without having the air quality impact, can be kind of in a different category. And you're right, if you think of this as a zero-sum game and there's a finite amount of effort we can put into the environment, then you have the potential for people saying, we're not going to do this anymore because we're doing this. But if you think of the larger societal will to do something, when people pushed for a doubling of the NIH budget, it didn't push one disease out at the expense of another. It sort of ramped up the entire thing. And so I'm optimistic that could happen, but I do agree that we need to be careful that the opposite doesn't happen.
Question right here from Peter.
I was thinking about Bob's comment. It seems to me, and I think you mentioned this, that this, I think, brings more people on board to be able to do something than we have right now just to concentrate on CO2. And also, I think one of the great problems in protocols that we try to have is that everybody can always point to the developed world saying they're the major producers of CO2. But now, there is something tangible that the local nations can do for things that they are doing themselves and to improve their life. I think this is a very, very sound idea.
We talk about in political negotiations sometimes things like confidence building measures. And that's another thing that I hope that this, the developing world and the developed are on the same side on this issue. It's not a finger-pointing thing of who should take a greater share. Everybody wants these pollutants to come down in the developing world. And the wealthier countries can help provide technology and expertise and financing to make that happen. But it really is, like you're saying, it's in those countries' own interests to do this. And maybe if we get some agreement and cooperation, that will extend to some of that goodwill towards reducing CO2 as well.
Okay. Thank you again. Let's thank Dr. Schindel again.